All right, let's head into the organic chemistry lab. Today, we're going to get a handle on a technique that sounds pretty simple, but it's actually one of the most powerful clues a chemist has in their toolkit, the melting point experiment. This is how we figure out if we really made what we were trying to make and just how pure it is. So, picture this. You've spent hours in the lab, you've followed every single step of the procedure, and now you have this little pile of white crystals. Is it the right stuff? Is it clean? These are the exact questions every single organic chemist has to answer every single time. And this is where we get to be chemical detectives. Our number one clue for solving this little mystery, the melting point. Yeah, it's just a physical property, but trust me, it tells us a ton about our sample. So here's our game plan. First, we'll get into the why behind the melting point. Then, we'll gear up with our lab tools. After that, I'll walk you through the procedure, show you what to look for, and finally, how to put all the evidence together to crack the case. You ready? Let's do it. First things first, let's talk theory. Seriously, understanding why this works is going to make the how make so much more sense. You got to know the science before you touch the equipment. So what even is a melting point? Well, here's the thing. It's not actually a single point. It's the range of temperatures where a solid goes from, solid to completely liquid. And for us chemists, it does two incredibly important jobs. It helps us identify what we've got, and it tells us how pure it is. Okay, this is the key idea. A pure compound has this perfectly organized crystal structure. Think of it like soldiers standing in a perfect, rigid formation. It takes a very specific amount of heat to break up that formation, right? So it melts over a very tight or sharp temperature range. But now, what if you have an impure compound? Well, those impurities are like random civilians wandering through the soldiers' ranks. They mess everything up. This chaos weakens the whole structure, so it takes less energy to start melting, meaning the melting point is lower or depressed, and the whole process is messy, happening over a much broader range of temperatures. All right, so we've got the theory down. Now let's get practical. It's time to assemble our toolkit for this investigation. First up, you're going to need a watch glass and a spatula. Simple enough. Your main job here is to take those crystals and gently crush them into a fine, consistent powder, almost like sand. This is super important because a fine powder heats up nice and evenly, which is what you need for an accurate reading. Next, we have the capillary tube. It's this tiny, super thin glass tube that's sealed at one end. You just tap the open end into your powder to pack a little bit inside. You only need about 2 or 3 millimeters high. This little tube is where all the action is going to happen. And of course, the star of the show, the melting point apparatus. This is the machine that does the work. It's got a heating block, a thermometer, and a little magnifying glass so you can get a front row seat to watch your sample melt. We've got our theory, we've got our gear. Now let's walk through the actual procedure. And listen, precision here is everything. If you want to get evidence you can actually trust. So let's go through the method. Once you've prepped and loaded your sample, you're actually going to do this twice. The first run is just a quick and dirty scout mission. You heat a sample really fast to get a ballpark idea of where it melts. This just saves you a bunch of time. Then, with a totally fresh sample, you do the real run. As you get close to that ballpark temperature, you slow the heating way, way down, like only 1 or 2 degrees per minute. Why so slow? Because you need to give the thermometer time to keep up with the sample's temperature. If you heat too fast, your thermometer will lie to you, and your whole result will be wrong. That slow, patient approach is the secret to getting good evidence. Okay, now we're at the most critical moment, the observation. You need to be glued to that little eyepiece, watching your sample like a hawk. You are looking for 2 specific data points that will define your melting range. And I'm going to say this again because it's that important. You are not looking for a single melting point. It doesn't exist. You are recording a melting range. That means you have to write down 2 different temperatures. Your first temperature, let's call it T1, is the exact moment you see the very first tiny drop of liquid show up in your solid powder. Sometimes it looks like the powder is just starting to sweat. That's your cue. Write that temperature down immediately. Your second temperature, T2, is the point where that very last little speck of solid finally disappears and the whole sample in the tube is just a clear liquid. That's your finish line. Record that temperature. The range from your T1 to your T2, that is your final crucial piece of evidence. Okay, detective, we've collected our data. The suspense is killing me. The case is about to be solved. Let's figure out what that T1 to T2 range is actually telling us.
So here are the three possible verdicts from our investigation. Scenario 1, your range is sharp. We're talking less than 2 degrees wide, and it perfectly matches the known literature value for your compound. If that happens, boom, congratulations, you almost certainly made a pure sample of exactly what you were aiming for. Scenario 2, your range is broad and the whole thing is lower than the known value. Uh-oh, that's a classic sign that your sample is impure. And finally, Scenario 3. What if your range is sharp, but the temperature doesn't match the known value? Well, that means you probably made something that's pure. It just isn't the compound you thought you were making. Time to recheck your notes.
And that leads us to one last question. Let's say your evidence points to an impure sample. The case isn't closed. It just moves to the next phase. As a chemist, what's your next move? Well, you'd move on to purifying it, probably using a technique like recrystallization. But that, well, that's a whole other case for another explainer.